Hey, Dietrich Labs, Sam here. In this video, I'm going to show you how to solve the Einstein field equations for the Reissner-Nordstrom metric. This problem has many similarities to the problem of solving the Einstein field equations for the Schwarzschild metric, and seeing as I have already done a video on that process, I will use results arrived at in that video to significantly speed up the process here. A link to my Schwarzschild metric video is in the description. For those of you who have issues and don't remember what the Einstein field equations are, they are right there. We obtain them by taking the Ricci curvature tensor, subtracting from it a half the scalar curvature times the metric, and then adding to it the cosmological constant times the metric, and then setting that equal to 8 pi g over c to the fourth times the stress energy momentum tensor. The Reissner-Nordstrom metric describes nearly the same space-time geometry as the Schwarzschild metric. The one key difference is that the black hole at the center of space-time is now charged. Therefore, we can start setting up the problem by making this one key alteration to the Schwarzschild assumptions presented in my last video. These slightly altered assumptions will be referred to as the Reissner-Nordstrom assumptions. The Reissner-Nordstrom assumptions are as follows. No vacuum energy, and the only thing in the space is a charged, massive point singularity. The vacuum and the metric is spherically symmetric and static, and it's Lorentzian because special relativity doesn't just go away because you've got a gravity field. Okay, for reasons explained in my Schwarzschild metric video, this immediately gives us the fact that the cosmological constant is 0, and it also gives us a convenient ansatz. So first, no vacuum energy gives us that. Then this assumption actually gives us this metric ansatz. It's not totally trivial how it does that, and the explanation I gave in my video on the Schwarzschild metric. It comes from parts of the assumptions that are the same between the two cases, so the ansatz ends up being identical. Let's see, the addition of charge, however, does change a few things. First, the stress energy momentum tensor is no longer 0 because the vacuum now contains the electric field produced by a singular point charge. The stress energy momentum tensor is now the Maxwell stress energy tensor for an electromagnetic vacuum. With this specific stress energy tensor, the Einstein field equations become the Maxwell-Einstein equations. The stress energy momentum tensor reads that. It's just a standard Maxwell stress energy tensor that you have doubtlessly seen before. Okay, the fact that the black hole is charged technically means that the complete equations describing the system are the Maxwell-Einstein equations coupled to the Maxwell equations in curved space. So, for the general case, we would have to solve this highly coupled system of equations simultaneously, which is very difficult. However, for the special case of the Reissner-Nordstrom metric, there's a clever trick that we can use to break the problem up. Because the electric field is the result of a point charge sitting at the center of a gravity field with exactly the same spherical symmetry, the presence of the gravity field would not have any effect on the form of the electric field. Therefore, the four-vector potential must just be the Coulomb potential. So we've got that. It would just be the Coulomb potential. So that's the D that we get out of this. That's the fourth conclusion we get out of this. So this is the last deduction that can be made purely from the Reissner-Nordstrom assumptions. Because the solution to the Maxwell equations for this system could be deduced straight from the Reissner-Nordstrom assumptions, our task has been reduced to just solving the Maxwell-Einstein equations. From here, the next step in solving the Maxwell-Einstein equations for the Reissner-Nordstrom metric is to evaluate the Christoffel symbols for the ansatz given previously using the standard formula right here. So again, doubtlessly you're familiar with that. Certainly if you've watched my video on the Schwarzschild metric UR. Okay, so because the metric ansatz for this problem is the same as the one for the case of the Schwarzschild metric, the Christoffel symbols written in terms of the unknown metric functions have exactly the same form. Because I computed all of the non-zero ones in my video on solving the Einstein field equations for the Schwarzschild metric, I am just going to list the results here. If you want to see their calculation, you can watch my video on the Schwarzschild metric. All of the non-zero Christoffel symbols are in this box. There are 13 of them. The other of the total 64 are 0. You can calculate them on your own time. But those are the values of the 13 non-zero ones in terms of the unknown metric functions. So I also showed the calculation of the Ricci curvature tensor for this metric ansatz in my Schwarzschild metric video, and will therefore just list the results here as well. The formula used was the standard one, this one right there. It's the one that was used, so just the ordinary one for the Ricci curvature tensor in terms of the Christoffel symbols. So for our ansatz, as I worked out in that video of mine, you get this for the Ricci curvature tensor. That's the result you get. So then, before proceeding with this metric ansatz, it is fruitful to look at the Einstein field equations themselves for this problem. So the Maxwell-Einstein equations, which are just those. The trace inverted equations happen to be easier to work with here because the Maxwell stress energy tensor is traceless. So the trace inverted equations for the totally general case, even with a cosmological constant, are those, which again, hopefully you've seen those before. So because the trace of the Maxwell stress energy tensor is 0, and we're ignoring the cosmological constant as per the first Reissner-Nordstrom assumption right there, which leads to that, then this ultimately collapses down to this. Now, for the general case, obviously you don't have this relationship that the Ricci tensor is proportional to the stress energy tensor. But in this case you do, but only because the stress energy tensor happens to be traceless for this case. So this means the scalar curvature need not be calculated because it doesn't show up in these equations. This is why I placed this discussion just after calculating the Ricci curvature tensor. We can therefore move on to computing the Faraday tensor and the stress energy momentum tensor. The Faraday tensor is a bit weird because even for a generally curved space, covariant derivatives are unnecessary because the Christoffel terms cancel. So that looks like this. You can see here we insert the covariant derivatives to get the Christoffel symbols, and they cancel for the general case. So they're not needed. We can just use this formula here. So now the next step is to insert the vector potential that we had, the Coulomb potential, to get the Faraday tensor. So just plugging it in or if you remember, the Coulomb potential is this, then we got that. Right, okay, so then plugging that into the formula for the covariant component just gives us this, where we get the second non-zero one by using the antisymmetric properties of the Faraday tensor. All the other components are 0, so that's why you only see them 2 calculated there. So then using index juggling to calculate the contravariant components gives us these results. Then writing this all in matrix forms, we've got then this result for the Faraday tensor. So with that calculated, now we need to compute the stress energy momentum tensor. It is useful to start by calculating the square of the Faraday tensor because it shows up in the stress energy tensor. So we just contract indices, ignore the 0 terms, and then plug in the values for the non-zero ones. We get that, and we simplify to get this. Okay, so then we can plug that along with the values of the Faraday tensor for the first term of the stress energy tensor to get it. So this again is just the formula we're using as was stated before. Turns out there are only 4 non-zero components to this stress energy tensor for this vector potential. And they end up being this. The calculation proceeds quite beautifully for these four. Right. So then if we write this in matrix form, we then have this result here. This is the stress energy momentum tensor. So with that calculated, then, oh yes, it's actually worth pointing out, I said that it's traceless for the general case, which means it must be traceless for this case too. And in fact it is, but it's traceless only if we use the metric for the space it's written in, so the metric ansatz we started in. That's the natural metric, and it's traceless when you evaluate the trace for that metric. So now, because we've got the stress energy momentum tensor and the Ricci tensor, and we know the field equations that we're solving are just these, we've got enough to write out the equations for the unknown metric functions. When we do that by equating those two sides of the equations, we get this. We get those four equations there. So then these are the ones we're actually solving. These are the ones we need to solve to actually construct the Reissner-Nordstrom metric. These equations are almost the same as the ones for the Schwarzschild metric functions. The only difference is the presence of the source terms. Despite the source terms, the first step in solving them is nearly the same as for the Schwarzschild metric. The first step in solving these equations is the following. It can be shown that A and B are multiplicative inverses. This can be done by dividing the first equation by B and dividing the second equation by A, and then adding the two. So when we actually sit down and do that, so dividing the first one by B gives that, and dividing the second one by A gives that, and adding them gives that, and then simplifying that down gives us this right here in the box. Right, so that we're going to algebraically manipulate to get a useful, or to prove that they're multiplicative inverses. So the first step in doing that is integrating, which gives us this. Now adding the log of b to the other side gives us that, and writing it as the log of a product. Okay. So then finishing up the algebra, and we get this result. Exponentiating both sides in there, and then we get that coming straight out. So now we need to insert this into the third field equation, one we haven't used yet. And that gives us this right there, simplifying, gives us that. So now the entire problem is reduced down to solving this single linear first order equation. Much of the form of the solution to this equation can be worked out by remembering that the Reissner-Nordstrom metric must approach the Schwarzschild metric in the limit of zero charge. So then we can set the b function equal to the value of the b function for the Schwarzschild metric plus some charge-dependent alteration, where that charge-dependent alteration goes to zero in the limit of zero charge. Written out, that is just this. So if we plug that into the equation for the b function for the Reissner-Nordstrom metric case, then it gives us an equation for the f function, which is just the thing in the box here. It's that, if you plug it in. So then this is such a ridiculously simple equation, we can solve it just by looking at it by inspection, and that's the result we get. Okay, so then now we've got that, we can plug this into that to get the b function, and then we can plug the b function, we can take its inverse and get the a function, and that'll give us the unknown metric function. So then written out, these are the unknown metric functions, but this is the whole thing we've been going for the whole time. So that means we're done, because we can get the Reissner-Nordstrom metric now just by plugging these values in for the unknown metric functions. When we do that, we get this gorgeous thing. It's the Reissner-Nordstrom metric. The line element is this, so this is the famous result. That is the Reissner-Nordstrom metric. It's a line element, and that is how you solve the Einstein field equations for the Reissner-Nordstrom metric. D-trick out.